All right. Hi, James Key. This is how I do this. Just pick a function, f of x equals x cubed minus 33x squared plus 216x. Okay, I'd like to know everything about this function, where its roots are, where it is increasing and decreasing, where it's concave up and concave down. Alright, so I basically just need to do a lot of math. One thing I could do is I can factor this function. It turns out I can't always factor a cubic, but I can factor this function. And here's a quadratic, which in principle I can solve if it has roots. But this particular quadratic, I think, has been pre-chosen to be factorable. So 216 is 6 cubed, but maybe I'll just make a quick factor tree. So this is 108, 54, 27, and like so. So what are the factor pairs of 216? 216, 1, 108, 2, 3, and 72, 6, and 36, 9, or rather I guess 8 comes next, and 27, 9, and 24, and I think that's the one that I want. So this function is in fact x, x minus 24, x minus 9. So that's kind of nice. Alright, let's take the derivative of this function. Well, the derivative of this function is, going back up to this form, 3x squared minus 66x plus 216. I think I can factor a 3 out of this, so I get x squared minus 22x plus 9 times 72. Yep. And I think that's also factorable. Oh man, let's see. Can I do this quickly? 72, 1, 2, 36, 3, and 24. So that doesn't quite work. 4 and 18. Yep, that's the one. So the first derivative is 3x minus 18x minus 4. And finally, I will take the second derivative, and the second derivative is using this form, 6x minus 66. And so this is just 6x minus 11. Okay, so now that I've done all that work, I can begin to analyze these. So what we're going to do is we're going to make some nice number lines. Well, I'll first make a number line for the function. And what I have just learned is that this function has roots at 24, at 0, and at 9. 0, and here is 9. And because this is a cubic, and because the leading coefficient's positive, it means the end behavior is going to be like this. And because it changes sign at each one of these numbers, 0, 24, and 9, I can be sure that it's going to go negative, positive, negative, positive. I will also look at the sign chart for the first derivative. And by the way, this cubic is nicely factorable, so I've spent time finding its roots because I could. Sometimes it's not so easy to find the roots of a function, so we skip that step. But this step is crucial. It's the step where we look at the signs of the first derivative. Now, we factored that as this quadratic here, so it's going to have a root at 4 and at 18. And because this is a quadratic and the end behavior is like this, and it changes sign at 4 and 18, I know it's going to be positive, negative, and positive. Which tells me that my function is going to be increasing here, decreasing here, and increasing here. That's important and valuable information. Let's get to the second derivative. The second derivative is just the line 6x minus 11. Well, that is going to change sign here at 11, and it's going to be negative before 11 and positive thereafter, which means that my function is concave down and then concave up. Okay, finally I put it all together and I make another number line, the f number line, and the f number line is the superposition of the f prime and the f double prime number line. So wherever f prime has a root or f double prime has a root, I'm going to put a number there. So this is 4, this is 11, and this is 18. And now I'm going to draw a representative iconic little picture of what a function, a generic function looks like on each one of these 4 intervals. For example, on the interval from negative infinity to 4, my function is going to be increasing and concave down. Well, what does an increasing concave down function look like? It looks like this. Between 4 and 11, my function is decreasing and concave down. What does a decreasing concave down function look like? It looks like that. Between 11 and 18, my function is decreasing concave up, and a decreasing concave up function looks like that generically. And from 18 to infinity, my function is increasing and concave up, and increasing concave up functions look like this. So we do a bunch of algebra, we do a bunch of calculus, we do more algebra, and then we make a number line, and that's going to really, really help us graph this function. So what does this function look like? Well, some of these numbers are going to be quite big, so I'm not going to waste time plugging these numbers for 11 and 18 into my function. But I do know that way out here at 24 is a root. And there's also going to be root at 0. And there's also going to be root over here at 9. I know at 4 there's going to be a relative max. So I'll just put that up here somewhere. And at 18 there's going to be a relative min. So I'll put that down here somewhere. Relative max, relative min. And more importantly, what I learned is that there's a point of inflection at 11. And what happens there is that's where the function changes concavity. So what does this function look like? It's going to be increasing concave up, then increasing concave down, then decreasing concave down until 11. So it's right here or something at this point 11 when the concavity of my function changes, something like that, and then back up again. So pretty much I know that my function will be concave down here and concave up here. All right, and that is the simple approach to making number lines and curve sketching. Okay, bye James Key.